Welcome to the deep dive. Today we're digging into some really fascinating research. A new record for universal quantum computer simulation.
That's right. We're talking about the JUQCS50 simulator. It ran on the Jupyter Exascale supercomputer and successfully simulated 50 qubits.
And simulating 50 qubits is a huge deal. Why is that specific number so difficult to cross?
Well, it's all about the memory. The computational requirements for quantum simulation are just absurd. If you want to store the state of n qubits, the memory you need doubles for every single qubit you add. It grows exponentially.
So you hit a wall, a very, very hard wall.
A very hard wall. We're talking about needing so much memory that, crossing that 50 qubit threshold was seen as almost impossible without some kind of extreme innovation.
So our mission for this deep dive is to unpack the 3 breakthroughs that let them smash through that exponential wall. They actually achieved an 11.4-fold speed up over the previous record, which was just 48 qubits.
An incredible leap.
Let's start with the hardware. Innovation number 1 is all about unlocking hybrid memory.
Exactly. So the Jupyter system uses these NVIDIA GH200 superchips. And what's special about them is they tightly integrate a really fast GPU with about 96 GB of memory and a CPU, which adds another 120 GB.
But the GPU memory, the fast stuff, wasn't enough on its own for 50 qubits.
Not even close.
And the CPU memory, the LPDDR5, that's usually known for being slower, right? Higher latency.
Correct. It's typically way too high latency for the kind of intense parallel work a GPU does.
Yeah.
But here's the clever part. They use this ultra-fast 900 GBs link between the two, the NV link.
Oh, okay.
And that let them treat the slower CPU memory as a kind of high-performance extension. They built this custom solution with an on-the-fly look-ahead optimizer.
How risky is that? I mean, when you start bypassing the standard operating system's memory management, doesn't that usually lead to, crashes?
It's complex, for sure, but it was essential here. This custom technique was the key. It delivered an 8.3x speedup compared to just using standard methods. It really shows you have to get under the hood of the hardware.
Incredible. Okay, so even with all that extra hybrid memory, they still needed to cut the total memory footprint by a factor of 8 to actually fit the 50 qubit state.
Yep.
And that brings us to innovation number 2, adaptive data encoding.
This is the critical compression step. Instead of using the standard 16 bytes for each number, they developed a way to represent them with just 2 bytes.
Wow, from 16 down to 2.
It's a massive compression. And it's what finally allowed the simulation to physically fit into memory and run.
Yeah, so you've won the battle on memory, but are you paying the price in time? I imagine there's a lot of overhead encoding and decoding every single state element during the run.
You are, but it was absolutely necessary. The gain from being able to run a 50 qubit circuit at all far outweighs that computational cost. It was a compromise they had to make to hit that scale.
Okay, so memory is solved, but now you have what sounds like a staggering coordination problem. We're talking about 16,384 of these superchips all working together.
Without a doubt.
Surely communication becomes the next huge hurdle.
It's the new bottleneck. If you have that many processors all talking to each other, the time spent just sending data back and forth across the network can kill your performance.
So innovation number 3. Communication optimization.
Right. They implemented an on-the-fly network traffic optimizer. It basically looks at the quantum circuit and figures out how to minimize the time spent on all that data exchange between the chips.
And there's a fantastic real-world example of this, isn't there? The adder circuit.
Yeah, this is a great illustration. When they simulated adding 2 25-bit integers, they found they could drastically cut the execution time just by relabeling the qubits.
Just by changing their names, essentially.
Essentially, yes. Just to minimize how much data had to jump between different GPUs.
Yeah.
That simple change dropped the runtime from almost 2,000 seconds down to about 1193.
That's a massive speed boost just from sorting your work more efficiently.
Exactly. And if we connect this all to the big picture, the main finding is profound. By combining all these innovations, the total time to simulate these quantum circuits, it no longer grows exponentially.
It's not that doubling curve anymore.
It's approximately linear. And that fundamentally changes the entire economics of quantum simulation.
So what does this linear scaling actually mean for you, the quantum development community out there?
It means JUQCS50 can now run exact high-accuracy simulations of key algorithms like VQE and QAOA 4 systems up to 50 qubits. We can get precise classical results to use as a benchmark to check if the real quantum hardware is working right.
And as we wrap up, here's something to think about. This simulator can now tackle problems that are 500 to 1,000 times larger than what other systems handle. But look at that adder example again. the fact that you can get a huge speedup just by relabeling qubits. It suggests that optimization at the algorithmic level is now becoming just as critical as the raw speed of the hardware itself.